Today, we're going to be speaking about knowledge distillation, which refers to a category of techniques aimed to improve the performance of small models. Let's dive into some motivation for knowledge distillation. So the goal of knowledge distillation is really to find a way to make these smaller, more efficient models have the performance of larger, more expensive models. So if we think of this graphically, let's consider we have two axes here. We have performance on the y and we have expense on the x. And we can think of expense here as including things such as the compute required, so the number of GPUs that you need, the latency, how long it takes to generate an answer, etc. In that x-axis, effectively, what we're considering is all of the expenses associated with large models. So if we put this into four quadrants, we can think of the following demarcations. On the left-hand side, we have the effectively cheap models. And depending on where they are above this horizontal line at the middle here, they're either performant or low quality. And on the right-hand side, we have the equivalent, but for expensive models. So if we think of our large language models, so this is like 400 billion plus parameters, so things like GPT-4, the latest Llama release, etc. We'll categorize this in this top right quadrant here. They're extremely performant, but they're also very expensive. And we're going to classify this type of model as a teacher model in the context of knowledge distillation. We then also have what we're going to refer to as our student models. These are smaller models, so they're not expensive to run, but typically they don't have the same level of performance as these larger, more expensive teacher models. So this might be an open source equivalent or just a smaller model. So for example, a Llama 7B or a Mixtral open source model, these smaller size models that you can compute and perform inference over just using consumer grade GPUs, but they don't have the same level of performance. Now what we would really like is to find a way to take the performance of the teacher and the efficiency, the cheapness of the student, and find a way to get a middle ground, which is a improved student model that as much as we can maintain the performance of the teacher without sacrificing the expense benefits of these smaller models. That is the motivation for knowledge distillation. Knowledge distillation techniques aim to try and achieve this dotted circle here, this more performant, smaller model. There are three main categories of knowledge distillation that we're going to speak about today. The most basic and ones that you've probably already used before is supervised fine-tuning. We also have a broad category of techniques that we're going to branch into divergence-based methods here. And finally, we have reinforcement learning approaches. These latest reinforcement learning approaches seem to be having the best outcomes, the best results on training these student models. So that's a high level for the motivation of why we need to do knowledge distillation. It's quite intuitive, and if you're practically deploying these features, you'll quickly realize how beneficial it is to have these smaller, high-quality distilled models. Let's dive into supervised fine-tuning. The process is very simple, so I'll go through it relatively quickly, but you can think of this as effectively finding a way to use the teacher model to get synthetic data that you then train the student model on. So here I have the example, a prompt and a set of examples. You can think of this as effectively our seed data. So it could be on a variety of tasks if you're trying to get general performance, or it could be in a specific subdomain if you're looking to build a more performant model for your specific use case. But effectively, we take these seed examples, we pass them to the teacher model. Again, this is our large model. This could be a GPT-4, a Llama 4 or 5B, and we get a series of answers. We store these answers in a database, so these are our source, our training material, and we take our student model. So we instantiate our student model, and then we take the examples that we've gotten synthetically from our teacher model, and we train that student model. We then effectively, once this training process is complete, we get a new student model that has some of the performance of the original teacher model, assuming that we have done this optimization process well. Important to note here, just from a practical perspective, is check the licenses of the models that you want to use for the teacher. There are some models that will not allow you to generate synthetic data for the purpose of doing exactly this, distilling smaller models. So it's important that you check the licenses associated with your models before you do this. Just to summarize here, if we were to write this down as a mathematical expression, this is just our standard loss function for training a large language model. And in this case, we're using it for the distillation process. And the things to highlight here in this equation, we can see we have this y is coming from PT. That is meaning that synthetic data that has come from the distribution associated with the teacher model. In the square brackets here, what we have is the log probability of the student model. But as you can see, it's the value y, the synthetic data generated from the teacher, conditioned upon x, which is that seed data. Okay, let's move on to the next category of techniques now, which are divergence based. We'll go through the same process again, where we give a high-level diagram of this flow, and then I'll provide a mathematical expression to solidify exactly how this process works. Effectively, the primary difference now between supervised fine-tuning before and these divergence-based methods is we introduce a new divergence function who has the role of adding a penalty term to your loss function, which will then motivate the student distribution from being closer to the teacher distribution. So it avoids effectively the student distribution from differing too much. Let's make it more concrete now. Again, we start off with our prompt and examples, our seed data here. In this case, we split off into two branches. We provide the data to both the student and the teacher in parallel. As outputs from these models, we get a probability distribution. So here we have the subscript T for the teacher and the subscript S for the student. An important caveat at this point here is we're assuming that the teacher is something that we call a white box model. A white box model means that we can have access to the ultimate probability distribution generated by the language model, as opposed to a black box model in which we only get the output tokens. So assuming we have a white box model, there's a lot more that we can do, and we can do these divergence-based methods. Practically, white versus black box models would be, for example, OpenAI's endpoints, which are black box. They do not provide you the probability distribution in most cases used for the generation across all the tokens, versus a Llama 405B, which has open weights and you can get the distribution yourself from this outer layer. Okay, coming back to the diagram, we now have our generations for both the student and the teacher. We then provide this to D, where D here is representing this divergence function, and there are multiple that you could choose here. For now, just view it as an abstract method for calculating the difference in the distribution between two distributions, in this case, the teacher and the student distribution. What we'll also typically do is for our student, we'll also calculate the cross-entropy loss, or just a general loss based on the tasks that we're looking to perform for that base model. We will then combine both the divergence loss and the original cross-entropy loss to calculate our overall loss function. We then have our loss function and we upgrade our student distribution using backpropagation. So we take the gradient of the loss with respect to the parameters of our student model. Ultimately, once this process is done, assuming that we've been able to converge, we will have now our trained student model, which is going to be more performant at its task while remaining its efficiency, and also with the added benefit now of we have mathematically imposed that the distribution of the student model should still be relatively similar to the teacher distribution. This avoids the student model from being able to hack our objective function, and instead as well make sure that we take into all of the nuances that the teacher model has been able to learn over its trillions of tokens of training data. Mathematically, we can express this as follows. Again, I've done this in a relatively abstract way. We have our divergence function here represented by D, which is taking in the probability distribution of our teacher and our student. The data is the same, Y and X are the same there. And we also have the second term, our cross-entropy loss. We introduce two different hyperparameters here, which is alpha and beta. So for simplicity's sake, let's say if beta was 0, then this would only be calculating the divergence between the student and the teacher model. But in practice, and how this was traditionally motivated, is we included both of these terms in our overall objective function. Okay, so that's a high-level overview of how the divergence-based methods work. Let's talk about two concrete divergence functions. And that is going to be forward and backward Kullback-Leibler divergence that we'll primarily speak about because these are used most often. So let's start with forward KLD. The high level important thing to note here is with forward KLD, we can induce this mean seeking behavior. And often this is actually not desired for the task of language generation. I'll show a diagram, this will become more concrete, but just keep that in mind for the moment. The backward KLD instead invokes mode seeking behavior. This, for the language modeling task, is going to be more beneficial, but it will have impacts on some of your sampling techniques for actually getting out your tokens. So for example, if you're doing a greedy-based approach where you're taking just the most probable next tokens, this is going to be quite beneficial. But if you're going to use some more advanced approach where you're not necessarily taking the most probable next tokens, backward KLD could have some issues here. Let's see this visually, because then this mean and mode seeking behavior is going to make more sense. It's also important to note that this KLD diagram, this KLD function is not symmetric. So forward and backward implementations of the two actually have different results, which you'll see graphically. So I've taken this graph from the paper, and you can see it in the footnote at the bottom here. We have our target distribution in blue. So this is some general function, but you can think of when we're training an LLM, there is in general this function that we're trying to optimize. And we've run forward KLD, which is the dotted orange, and we've run reverse KLD in green. We see in the forward KLD this mean seeking behavior. You can see if we assume that over the axis here, we have a probability distribution of tokens, you can see that we're assigning more probability weight across the tokens if we're thinking in terms of LLMs. And for the reverse KLD, what we're instead doing is we're focusing on that mode of the original target distribution. Now, for the context of an LLM, you can think of if we're generating text, there are likely going to be some tokens that in general for the teacher are going to be more probable, but there'll be modes throughout. So there'll be these peaks throughout like this blue distribution. If we do the mean seeking behavior, which is from forward KLD, then we'll disperse a lot of our probability for our student across these modes, which will mean that we'll often probably get bad generations, because we'll take, for example, words that wouldn't practically from a human perspective come next, but because we've done this mathematically and we're doing a probability-based approach, we'd still sample them from this forward KLD approach. Backward, or reverse in this sense, is going to be just focusing on the most probable tokens from your teacher model, which for most of the cases with language generation is going to be what we want. So we're going to lose some flexibility, but what we're going to have is a student model that is better at doing what is the base task of just predicting the most probable tokens occurring based on the teacher model well. Practically, from a user perspective, this is often the better, and this is also shown empirically on benchmarks for LLMs. I'll also briefly show you, for reference, the function formulas for both forward and reverse. And you can see here as well why I also highlighted that this is not a symmetric function, which means that our forward and our reverse will actually have different implementations. Whereas you can see it's actually very simple to switch between the two, and that's just changing the distribution for the parent and the student, P and Q. Okay, so that's the main methods for calculating this divergence in the divergence-based approaches. Let's now talk about reinforcement learning-based approaches. In particular, I'm going to focus on DPO, as this is probably going to be, from a practitioner perspective, the easiest to implement and is also seeing good results. Alternatives would be PPO, motivated by OpenAI. You can read on that information as well, but for this presentation, we'll focus on DPO as a representative example of distillation-based reinforcement learning. There are effectively three stages as motivated by DPO in the paper Zephyr, again at the footnote here. Let's start with the first. The first stage is just doing this supervised fine-tuning that we've already gone through before. So I have the diagram here. What we're doing here now is taking this original teacher model, and what we're generating is a student model, which I'm calling now SF to demarcate it from our subsequent student models. But effectively, this first base is we get a student model that has been fine-tuned based on the teacher. We then move to stage 2, where the objective here is to obtain preferences. So we're trying to find rankings between what is preferred. So one way that you could do this, for example, is in reinforcement learning with human feedback, where you get humans actually to do this process of ranking the outputs. And that has obviously been done to great effect in most of the ChatGPT style settings that we see today that are used most widely. These have all been based on a process of doing further reinforcement learning with human feedback. Another option, which is used in this DPO process, is to use AI to do this ranking. So let's start with an input and a prompt. This is our seed data to the model. What we'll do is we'll provide this to a series of n distinct LLMs. We will then get n distinct answers. So we now have these answers, and what we do is we provide them to our LLM, our evaluator, our judge, whose purpose is to rank the answers based on preference. So which one is better? What we get as output of that is a ranked set of answers, and I'm ranking here from left to right. So we'd say that answer 3 was the winner, and in the nomenclature of this paper, the others would all be considered losers. So effectively, you can think of this though as the output as being a ranked set of preferences from the LLM. Now, one other approach to do this, if you don't want to do the evaluator step, which can also include costs, is to naively choose a model, a teacher model that you think is best. So for example, this could be a GPT-4, and then take a series of other models. This could be example, original smaller Llama 2 models. And you just say that whatever was the generation from GPT-4, we're going to say that is the winner, that is the best. So that's a more naive way of doing that. And to pause here and consider why we're actually getting these rankings, it's important to note that just the fine-tuning process often will actually not be as performant on benchmarks, and also from a qualitative perspective, which we've seen based on leaderboards with human feedback, where humans are looking at these. So this ranking process of obtaining the preferences is often the secret sauce of creating what is a really good chat-based model. So for things where we're doing interaction-based with users, often this next step of doing this preference, of obtaining these preferences, will improve your performance significantly. Okay, so now we've got our first 2 stages done. Recap, stage 1, we did our supervised fine-tuning. Stage 2, we're obtaining our preferences. In stage 3 now, we need to distill these preferences. So our objective here is for our student model to effectively learn the preferences from the teacher model. So our student model should be able to generate output that is going to be preferred to other examples. So its job here is to learn these preferences and assign higher weight to winning outputs. So our input to this stage is effectively a combination of the input and prompt, and our winning answer and any random losing answer. So as you can see here, we're directly taking the same input and prompt from our stage 2 model. We're also taking answer 3, which was our winner, and a random answer, answer K, as our loser from the output of stage 2. We then pass this as input to our SF, which is our prior now reference model that we did the fine-tuning process, the supervised fine-tuning process over, and also a new student model that we're trying to optimize to learn these preferences. We take this output and we pass it to our objective function, which is a special objective. I'll talk about this more later. And just like normal, we do a backpropagation process based on the gradient of this DPO objective and update the weights of the student model according to this gradient to get our ultimately trained distilled student model that now also has knowledge of ranking and preferences. So it can output content that is going to be more preferred according to our preferences obtained from stage 2. The DPO objective is nuanced and different to what we'd normally do for just a cross entropy or negative log likelihood lost, in the sense that now we're dealing with rankings, and we need to find a way to factor these rankings and these rewards effectively into a mechanism that we can then train for our neural network. So in the subsequent slides, we're going to be talking more about how we can actually derive this DPO objective, and subsequently how we can do this gradient update. So let's move on to that now. So let's jump in now to derivations. And to start with working towards this loss, this objective function, we need some prerequisite information. So let's start with the Bradley-Terry model. So we take a optimal human preference distribution, which is this P star here. As we see, we're ranking 2 things, these Y1 and Y2. This Bradley-Terry model, which we're taking as given here, is a functional form to represent this preference distribution, where we also have this concept of R star, which is the reward model here. And our reward model is going to take in a prompt, so our X here, and our Y, which is the result, and it will calculate a reward value here, which is also leveraging this pi star, which represents a policy. Pi star is the optimal, pi ref is our base. So in the context of our language models, pi star is going to be the one that we fine tune and reference. Pi star is going to be the student we're fine tuning and reference the base. We also have just some general properties of dealing with exponentials here, which are going to be needed for our derivation. So here we're just multiplying and dividing by exponential of a on the bottom, and we can see then we can cancel some things out to get the following form. If you know the logistic or the sigmoid function, you're probably picking up that this looks very similar to that, except we have the wrong order for this exponent. So we can just change b and a here to get a form where this policy, this p star, is written now in terms of a logistic function. So as we now have these prerequisites, we can put them together to actually derive the loss function. So let's start now by looking through how we're going to define this objective. So our DPO loss is going to take in this pi theta, which is the student we're training, and the reference that we've already trained. And it's going to be an expectation over the prompt X, our winning response YW, and our losing response YL, which is all taken from our data set. And it's going to be taking the log of this preference distribution, this likelihood here. And what we're trying to do is make it so that our YW, our winner, ranks higher than our YL given the prompt. So that's the base of it there. We can now start substituting in information that we got from our preliminaries. Specifically, what we have for this preference distribution and what we have for the reward model R star. If we substitute in our work deriving for the logistics function, and then we're using R star, we can replace this with A and B. And what we're using here as well is our YW and our YL, so our winning and our losing. You see we also have this beta term, which includes Z of X. Z of X is just a partitioning function. I haven't spoken about it much because, as you can see right here, they actually cancel out. So it's not important for our perspective, which is just understanding this loss function for the DPO loss. So we have the primary bones of it here. If we can just rearrange and clean up the page a little bit. To highlight what we're doing here is effectively we are taking this pi theta, which we'll highlight in a second, which is going to be this student that we're trying to train. It comes from our reward model. We also have our X, which is our prompt, our YW, which is our winning response, and our YL, which is our losing response. We have as well our pi theta, which is the student, and our pi reference, which is the supervised fine-tuning results. So this FST should actually be SFT. That's a typo there. But effectively, we have now gotten our loss function for the DPO objective. What you can think of this from a practical perspective, if we're trying to implement this, is we take our already fine-tuned model and our student model. What we're going to be doing is also taking our X and our winner and our loser that we sample from our training data set. We are going to run it through both models, and we're going to calculate this loss function here. And what this is going to do when we take the derivative, which we'll see shortly, is we'll be able to find a way to effectively update the weights of our student model. So we're optimizing over the student model such that we rank these winning responses as higher than the losing responses, YW greater than YL, according to the Bradley-Terry formulation of the preference model. So let's now dive into the derivation actually of this loss function. And let's start by first taking the loss function. So this is just exactly what we had before. And let's take this component in the secondary square brackets and call it U. This is just going to make it easier as we're doing the derivations to follow, so that we don't always have to write out this long equation and keep that in our head. What we're going to do is we're going to take the derivative of this loss function with respect to theta. These are the weights that we're trying to optimize. And so simply, this is going to be the gradient of our expectation of log of the sigmoid of U, which is that term that we replaced before. Now, this isn't always the case, but for this specific case, it works out so that the derivative of the expectation is actually the expectation of the derivative, which is this E. So now the derivative becomes quite simple. We just leverage the chain rule, which I have on the right there for when we have a derivative of a function, and we can apply this to our terms as we go. So firstly, we're going to be taking the derivative of this log of the sigmoid of u part. This is just the standard derivative for a log, and also for sigmoid though, we can use the following. So the derivative of the sigmoid here is showing on the right. One more property we need to know, which is the sigmoid of negative u is actually the same as 1 minus the logistic of u. Sigmoid, logistic, they can be used interchangeably. So we can substitute this information in here, and we get the following term. So all there's left for us to do here in deriving this loss function, the derivative of this loss function, is determining how we can actually get the derivative of this u term. U is also a function here, so let's figure out how we can actually get the gradient vector of this. Effectively, we can move the beta outside because it is a constant when we're deriving and we're optimizing in respect to theta, because it doesn't depend on theta. And if you know properties of the log ratio here, then we'd see that this actually, the fraction turns into a minus, and because in the secondary term, which is using the reference, there is actually no theta there as well, it becomes irrelevant for the derivation, so we don't even show it in the second part here. We can now simply rewrite this by taking the beta out the front, and we get the following term. So effectively now we have all the components that we need to derive the loss function in the same way that it is in the paper that originally motivated DPO. So let's rearrange this effectively, and then we'll just substitute in the information as required. So again, we're taking this gradient, it's over the theta, that's what we're optimizing over. Our policies there, theta being the one, the student we're training, that's representing that, ref the supervised training one from stage 1. And I've taken beta from the second term in advance. They're all multiplicative, so just moved it now here. This is just so that it aligns to the paper. So if you're looking along with the paper, it will appear the same there as it does here. So effectively now, we have this derivative, and we just need to sub in u, so I'm just rearranging here so that it fits nicely in the page. And once we add our closing brackets, we now have effectively our desired function. One minor change that is done for the paper is they represent this this beta log term here with a r hat. So this is our estimate of the reward function. If we use this estimate here through parameterization, then we can rewrite the equation using r hat instead, and we'll get the result that is equivalent to what is shown in the paper. So let's just write that out here now. And so again, just while we're paying attention here, that W subscript is for the winning result, which is from the stage 2 ranking of preferences, and L being losing, or in this case, just anything that wasn't the winner. There are some alternatives where you can do multiple rankings. This specific formulation doesn't consider multiple rankings. So here we have our derivative, and we can get some really interesting information. So in this component here, this is telling us that this will increase the likelihood of the winning response, while we're going to be decreasing the likelihood of the losing response. That's exactly what we want. We then have this term as well, which is going to effectively increase the strength of the update when there is a large difference between what is the desired ranking and our losing one. So effectively, what we are doing here is we are, via updating according to this derivative, we're going to be increasing the likelihood of our winning responses, decreasing the likelihood of our losing responses, and we're going to be weighting that based on how big the difference is between our desired result. Effectively, via the process of backpropagation, when we're doing this, eventually we'll be training our student to take into account these preferences from the teacher, so that once this process has been done numerous times and we converge, we should have a student model that is able to reflect these preferences. And so we should ideally then have a model that is both smaller, more efficient, but also retain hopefully a large amount of the performance of our larger model, enabling us to get the benefits effectively of both of those elements, efficiency and performance. Okay, so that has been an overview of knowledge distillation techniques. To recap again, why we do this knowledge distillation is because we want to take the performance benefits of large foundational models and distill that into smaller models that are easier to run, cheaper to run, more efficient, without degrading too much of the performance from the teacher models. The better your distillation process is, the less performance degradation you should see from your teacher to your student. Thank you again for watching. If you have any questions, feel free to email me at info@aragoai.com. Thank you.